Welcome everybody to the digital technology and its place in the grains industry session. So today we have four speakers for you. We're going to start with Emily Dahl from ABARES, and she'll go through the market outlook for the grains markets domestically and globally. Then we'll move on to some data technology and practice use of those integrated technologies around farms. And in that case, we'll have Tim Neale from Data Farming, Professor Craig Baillie from University of Southern Queensland, and Rhiannon Schilling from SARDI, the South Australian Research and Development Institute. So before we get into the session, I just want to do some housekeeping notes. So you can submit your questions and upvote them on the panel on the left-hand side of your screen. Live Q&A will be at the end of the session after all the presentations. So we'll try and get through as many of those questions as possible, but you can start loading those questions up during the session. If the speaker has given permission, you'll be able to find the slides on the resource tab, so you can download those if they're available. And the session will be recorded and be available under the session catch-up tab after 24 hours. So I'll go ahead and introduce the first speaker. So Emily Dahl is from ABARES. She's the industry economist working in agricultural forecasting and policy section. She's currently the coarse grains analyst and was previously the oilseeds analyst. And she's contributing to the agricultural commodities forecast publication. So I'll hand over to Emily, and she can take us through the first session. Thank you.
Good afternoon, everyone. My name is Emily Dahl, and it's a pleasure to be part of this session on digital technology and its place in the grains industry. I'll be taking you through ABARES Outlook for global and domestic grain markets. What I'm hoping to do is set the scene for our speakers to present some of the key opportunities surrounding technologies that will benefit the grains industry. Another large crop is forecast for this year, with wheat, barley and canola production expected to reach record highs. Favourable seasonal conditions across all winter cropping regions boosted yield potential, especially in Western Australia and New South Wales, which are Australia's two biggest crop-producing states. Winter crop production is expected to exceed 60 million tonnes. Favourable conditions during the summer cropping season are also contributing to the record forecast, with sorghum production expected to be the third highest on record. Along with record production, world grain and oilseed prices have increased strongly over the last year. This reflects tight global supply and strong world demand. This combination of record domestic production and high prices has boosted the value of Australian crop production and exports. ABARES estimates the gross value of crop production to reach a record of more than $30 billion this year. That's the national picture for grains and oilseeds. Now I'll take you through the three major crops produced in Australia. Starting out with wheat, wet harvest conditions in New South Wales led to significant quality downgrades, and the softer season in Western Australia has meant there's a higher proportion of wheat making the ASW grade, which is trading at a discount. This is reducing the export supply of high-protein wheat. However, the global supply of high-quality milling wheat is low. This scarcity is likely to close the gap between prices for higher and lower grades of wheat. Similar to wheat, Australian barley prices are benefiting from high world prices. However, Australian producers are receiving below world prices because they lost access to the higher value Chinese market. Australian barley is likely to remain competitive over the coming year, and exports are expected to remain strong. As for canola, drought in Canada has significantly reduced Canadian canola production, as well as tightening global supply. This has pushed canola prices to record highs, driving up the Australian price with it. Record Australian production and prices have boosted the value of Australian canola exports, and the value of canola production is expected to hit a record of more than $6 billion. Current prices are high due to tight global supply as a result of less favourable conditions in other parts of the world. World prices are expected to ease as world grain and oilseed production increases. However, if economic recovery from the pandemic is slowed because of ongoing supply chain disruptions, this would ultimately lead to higher fuel and input costs, meaning that world prices remain higher for longer. Over the medium term, the value of Australian crop production is expected to moderate from current highs, given a return to a more normal sequence of seasonal conditions. We know there's a high degree of uncertainty when it comes to economic recovery and climate conditions. There are other factors that lie outside our more certain forecasts which could weigh on global grain markets. For instance, uncertainty over the Black Sea production region is dominating grain markets. Russia and Ukraine are major exporters, so any disruptions could lead to higher world grain prices and contribute to price volatility. Following the import tariffs imposed by China on Australian barley, Saudi Arabia has now become the biggest buyer of Australian barley. This shows how the supply chain can respond to disruptions and also highlights the importance of free trade agreements. Climate variability could be much greater over the next 5 years, and technology will play a role in driving cropping productivity. I'm sure our speakers will now give us some valuable insights into the technologies that are likely to benefit the grains industry. Thank you very much.
Thank you, Emily. So our next speaker is Tim Neale from Data Farming. He's a manager and director there. Data Farming services over 26,000 farms across 50 countries with satellite imagery every 5 days. It's very interesting technology. Tim comes from a background where he's been involved in controlled traffic farming, auto steer technologies, mapping, drainage plans, all those sorts of good things. So let's start into that discussion with Tim. Thank you.
G'day, Tim Neale from Data Farming. We're an Australian ag tech business based in Queensland, and I'm going to talk to you today about the space race and how agriculture is finally benefiting from the huge increase in satellite information. I guess to give you a bit of a starting point, just to understand what's been happening in the industry, for those that haven't been following, basically there's been a 25% increase in the number of satellites just last year alone. That's an incredible statistic. It just shows how quickly this industry is growing. This is driven by the technology improvements and the lower cost to launch and build satellites, and the massive investment that's been going into the industry. And there's some speculation that we may achieve up to 100,000 satellites orbiting over us in the next few years. So incredible access to data that we've never seen before. And now we're at the point of actually getting high resolution data every single day available commercially. Also opportunities for video. So people, you can actually get live video feeds from satellite now. It might be over a particular event, a fire or an emergency or whatever, but that again has never been heard of before. We've also talked to another company who wants to image essentially everywhere in the world almost on an hourly basis. So incredible volumes of data being captured in the near future that have to be stored and processed, but that's the kind of thing that's happening. The new constellations, once upon a time, like NASA would launch, say, one satellite every 5 years or so. Now companies are launching hundreds, if not thousands of satellites in a single year. So these new constellations are covering huge areas, and I'll talk about some of those use cases soon. And the bands of light that we're getting, so that normally the satellites are cut up into slithers of light. We're getting, once upon a time we might have had a dozen bands of light information. We're now into the dozens or hundreds of bands of light, which enables us to discriminate things on the ground much more clearly than we've ever done before. And of course, with all this competition, the price is naturally going to drop. So we're going to get higher resolution more often, better bands of light for a lower price. So really good opportunities going forward. So I'm going to rapid fire now into a whole heap of use cases that we've been doing. I guess one of the key things we've been working on is actually getting this access to, getting this data out to farmers. And the Sentinel satellites from the European Space Agency, we're providing to any farmer globally for free. And this enables everyone to get on board and start using the technology that's available. We've now got 27,000 farms accessing satellite data over their properties every 5 days. What can we do with that? Well, I guess we're trying to get action, right? We're trying to change behaviour, and this is an example of a variable rate application map of fertiliser derived from the satellite data. 3 zones. Add your rates, put them straight into the machine, and that machine then automatically applies those rates of fertiliser based on the demand in the crop. So really exciting, really easy and exciting use case of the technology. Things like once we put multiple years together, there's good correlations with soil type and things like soil carbon. No surprise, you grow more biomass, you grow more soil carbon. So there's great opportunities to use satellite technology over multi-temporal satellite data to derive where to take your soil samples and carbon samples. We can get satellite data anywhere in the world. This is an example from the Philippines where we're imaging pineapples, where we're trying to help determine where the good and the poor areas are of the field and help try and alleviate that and see what's causing that problem and alleviate that to fix that up and even up the productivity. Also here locally in rice this season, we've been able to detect very, very small disease outbreaks in rice crops. And again, this is 80 centimetre resolution data, very high resolution, which we can task the satellite to capture over specific issues and areas. A little bit more coarser resolution now, so the 2.5 metre pixel resolution, so a bit more coarser, but this is a project we're doing with AgriFutures where we've captured during December and January, we were able to capture every rice farmer in Australia up to 10 times. Now each capture size was 1 million hectares. So the capability of these satellite systems is incredible, where we can capture high resolution over large areas multiple times and give almost real-time updates to farmers and agronomists on the ground to help them manage their crops. Another example of some high resolution work, detecting rubber vines, so extracting out values where that rubber vine is and enable site-specific treatment rather than just broadcast applications. This is good for cost reductions, but it's also really good for the environment. Harvest progress, because we can task the satellite in high resolution, we can see how much grain's been harvested. And this is an example of harvest this year where we're able to calculate how full the bunkers were and how much grain, based on the sort of volumes, we can actually calculate the tons of grain that have been harvested on a particular location. And this is good for people just to double check their numbers to see that harvest progress. We've done other things like predicting yield in sugarcane. Sugarcane is a biomass crop, so it's very responsive to correlations between the actual harvested yield and what we see in the satellite data. So for this example, we could actually predict the yield of the sugarcane using satellite imagery and provide almost live updates of how much biomass is there. So once again, trying to get the technology in the hands of the grower. We've done some work with the horticulture industry on fruit flies. Fruit flies is a major problem in southern states of Victoria, and we're able to correlate the fruit fly trapping data, so the density of the fruit flies, with thermal imaging from satellite. So once we knew that correlation, we then reapplied that algorithm back over the imagery to work out where the hotspots are likely to be and where they should be placing their traps. So, once again, trying to get the deep insights back into the hands of the users on the ground. Another thing, we were able to do, not just working at where the crop is, but where there's no crop. So where the fallow land is, and also what soil water is underneath that fallow land, so that seed companies, fertilizer companies, chemical companies can start planning their logistics around how much product's required in each area based on how much hectares is to be planted. So it's fallow spraying or fertiliser application. So really good opportunities to use that technology to help with supply chains and getting growers the sort of supply of products that they need to grow the crop. We've done some work like in Zimbabwe, pretty dry year last year, and we're able to detect every single paddock growing in Zimbabwe so they can understand how much crop's likely to come in from a food shortage point of view. We've done some work with, we're doing work at the moment with Queensland Government to determine area planted of different horticulture crops. This is broccoli, and we're able to show that, you know, in certain months there's 1,000 hectares of broccoli and other months there's none. So, you know, how does that impact on labour forces and workplace, you know, planning? What's the size of the industry? How much value is it for the economy? Those kind of questions can be answered all from remote sensing. We've done that too in South Africa, where we've detected corn and soybean areas, all for customers trying to work out how much crop's likely to come into the cooperative, and it gives them a good idea from above. And, you know, one of our problems in the past has been, you know, the access to data when it's cloudy. Well, now we can get high resolution data from radar, which penetrates through clouds. And this is an example from Southeast Asia, where we can see every single oil palm through the cloud at very high resolutions. It's 50 centimetre resolution. So technology that's never been accessible ever in the past. So in summary, I guess we've got a massive increase in the satellite numbers, which means we're getting cheaper, better detail, so more resolution, more bands of light more often. That's going to drive price down. So that's going to be great for agriculture. There's going to, you know, I've shown you there's hundreds of use cases for Earth observation and agriculture. And I guess we're really at the tip of the iceberg. I think over the next few years, we're going to see this availability drive whole heaps of new use cases, but we're going to need to do a lot more research and development before any of that is sort of realised. So feel free to get in touch with any questions. Thank you very much for the opportunity to talk to you today.
Thank you, Tim. Just a reminder to everybody that you can ask your questions using the menu on the left of your screen. So go ahead and do that, and we'll answer those at the end. That was a very interesting talk. Now, our next speaker is Professor Craig Baillie from the University of Southern Queensland. Craig has been an agricultural engineer. He has over 25 years of experience in agricultural research, development and extension. And he's going to talk to us about the developing technologies and the broader picture. Handing over to you. Thanks, Craig.
Well, hello, my name is Professor Craig Baillie from the University of Southern Queensland. And today I'd like to talk a little bit about game-changing technologies in agriculture. Over time, you will be familiar with various improvements in agriculture through ag technologies. And so we've been through a number of revolutions, if you like, where technologies have had significant impact in terms of productivity and profitability on farm. And so we're currently going through what many people would regard as Ag 4.0, but it's fair to say that we've probably been through quite a number of revolutions and mini revolutions around particular things, which is what the graphics on the right-hand side of the screen demonstrates. One of the things, I guess, about global ag production is we need to increase our production in relation to, you know, increasing population. And so where we see a lot of that occurring is through improvements with the ag land that we're currently producing from. So, you know, again, improving our productivity, improving our efficiencies, increasing yields, those sorts of things, versus increasing the land that we have under production. So I guess one of the key questions is then, you know, is there that potential out in the field? And so we do see in many areas that the difference between what the potential yield is and the actual yield there's quite a significant difference. And that suggests that yes, there is an opportunity to do more with less, and that it also suggests that it's probably the inadequate adoption of technologies or farming practices to be able to extract that. So that's where there's some opportunities and gains. The other thing, I guess, just to stress is that, you know, farming systems have become more intensive, and so the pressures, I guess, in terms of agriculture are more than just productivity, profitability, and so environmental sustainability is a key factor as well. there is a linkage between technology and productivity, and what we see here in Australia is that our larger farms tend to be more productive and more profitable, and so our higher revenue farms are only 20% of the total number of farms, but they do produce as much as 60% of the income and output, and equate to about 60% of the land under production. The important thing, I guess, too, is that if all farms across Australia were performing at the top 20, our agricultural output would be increased by 18%, and our farm income would be improved by 24%. And some work that ABARES have done in looking at the productivity on farm and linking that to technology suggests that yes, whilst the larger farms are more profitable and more productive, there's something different that's going on those farms. It's not just simply a matter of scale of economy. And so the suggestion is that the technology and the farming practices that have been adopted on those farms are quite different, and that provides an opportunity for others, I'd suggest. Well, the art of farming today is a complex process, and over 140 decisions a year are made, whether you believe that or not. Certainly the number is large, and so what does the future hold? Is it more complex, or perhaps it doesn't need to be more complex? And so the things that are playing out at the moment is we see machinery manufacturers in particular moving towards more automated components, and so as they move from automation to autonomy, there's value in the various components that have been developed, which we can exploit now and extract value out of. Whilst labour savings is often seen as a key driver for these sorts of innovation, it's really things like productivity improvements and the precision of operations which I'd suggest are the key factors. So looking ahead, some of the things that are sort of limiting our ability around these technologies will diminish over time as well, because there's been rapid development in sensors, machine perception, machine learning, artificial intelligence are all technologies that are moving at a rapid rate, which will see some of the hurdles, if you like, going to fully autonomous systems starting to evaporate. I wanted to spend a little bit of time talking about some of the technologies that we see in agriculture at the moment, and artificial intelligence and data analytics is certainly probably in the front of everyone's minds. And when we often think of data analytics or artificial intelligence, we're often thinking about smart, intelligent things. But AI is being applied to a whole range of different things, from data fusion, where we can extract insights out of fusing different data sets together and processing large amounts of information. Maybe developing decision support tools which can assist farmers in terms of the decisions that they're making, or even agronomists in terms of the recommendations that they might be making. And also using AI to connect farmers within a farmer network, so that it might be that through that connection you can get a better understanding of where to market your grain, or where to buy ag chem and other farming inputs at a lower cost. So much like we do here in Australia, where we use AI to find the lowest cost hotel, there's an opportunity, I guess, in agriculture to use those same sort of analytics to drive costs down as well. The other area that I wanted to focus on was farm management software, sensing and IoT. And whilst this is a category that's fairly well understood from a GIS or a farm management system perspective, I guess the key thing here is that many of the systems that are being developed, whether they're tractor based technologies or handheld devices in the field, where the landscape is moving is more connectedness of those devices, so that the information that you might be collecting in the field is interfaced with a GIS software tool. That GIS software tool is interfaced with the controller on a tractor, which then applies some sort of chemical or herbicide around what you've been monitoring out in the field. So here's an example of a smartphone app where we're looking at counting the number of aphids on a cotton plant, and this is some technology that's been developed by the University of Southern Queensland. The other area of importance is automation to autonomy, and whilst we've been doing that for some time, and in particular the machinery manufacturers have been collecting large amounts of data, and essentially that information has been used to inform machine diagnostics and condition monitoring of that machinery. But increasingly, there's opportunity to exploit other information that might be collected on farm as well. And so as the machinery passes the field, it's obviously collecting lots of information. And yes, there can be insights obtained from that, but I would argue that this is still a evolving area. And of course, the other thing that plays into the mix here is that we have ISOBUS standards in farming, which allows that interconnectedness, if you like, between different sort of coloured fleets and the machinery and implements that they're using. The other sort of interesting aspect around automation to autonomy and the future prospects here is that we're really at a development crossroads. And so current developments by machinery manufacturers are looking at increased performance density. So this is about getting greater value, greater utilisation out of the machine that you've got, adding more and more features to extract greater levels of autonomy. But also there's another sort of branch, if you like, around smaller swarm farm concepts that are a completely different form factor to, say, the traditional tractor. And so we're moving in a territory which is from highly automated components to more autonomous systems. So we see the graph on the right there that autonomy on farm will be informed by, if you like, a merger of various components that have been automated to realise a fully autonomous system. The other thing, I guess, that plays into this mix is different power options on machines, and particularly with automation and autonomy, an interest around electrification of this machinery as well. The final tech area is around novel farming systems, and I guess this is about really exploring farming practices at much more minute detail, and where we can control environments to the nth degree, we can monitor crops with greater precision, we can really control our farming inputs. And so whilst this might be seen to be out of the reach of more conventional farming systems, many of the sort of concepts that will be developed through these areas can be applied, say, onto a traditional grain farming enterprise. And so where we've moved from whole of field management to, say, subunit or zonal management, there's a real interest to understand the individual plant response to localised conditions, how that can be extrapolated to other growing areas, how we can exploit a lot more information out of the current practices that we do by looking at things in greater detail. I just wanted to leave a couple of key points, and that's really around all roads lead to productivity increases, and I think that's really important. But the other sort of disclaimer to that is that for tech to be adopted and for it to be successfully adopted, it has to be monetised and that value realised. And so that's one of the key points. And sometimes the opportunities for ag tech is not about increasing productivity, but it's actually reducing the cost of farming. And I've seen, over time that that's where most tech has been monetised to create that value. Certainly productivity and profitability equate to technology adoption, and we've seen that where our larger farming operations achieve that not because they're larger, but because they're doing different things and they've adopted technology in those enterprises. The other thing is that, beyond productivity and profitability, there's an increasing focus on other factors like environmental sustainability, and that's where technologies will also play out and inform what we do in agriculture. And finally, the mover and the shaker in my mind is really this move from automation to autonomy. So, as I said before, increasingly components on machinery and sensors and other things on farm, which will provide a more automated experience, will be merged into autonomous systems. So, with that, I'd like to leave you with those thoughts. Thank you for your interest.
Thank you, Craig. That was very interesting. So, so we've started out with the satellite mapping. We've talked about on-farm types of examples, and our next speaker is Rhiannon Schilling. She's from SARDIS. She's an agricultural scientist in the agricultural program at the SARDI Research Station. Her focus is on improving crop and soil management across low, medium, high rainfall zones. She's on a GRDC funded project to look at machine learning to extract maximal value from historical paddock data. So we're going to drill down into detail a bit here. So over to you, Rhiannon. Thank you.
Hi everyone, I'm Rhiannon Schilling and I'm here today to talk about the value of data sharing to enhance machine learning outcomes. The work that I'll describe today is funded by the Grains Research and Development Corporation, or the GRDC, and involves a project that's led by the University of Adelaide. As a bit of background, what we can see around Australia is that the amount of data being collected at a paddock level is increasing, and this is increasing in all different forms and types of data. So as an example, this is one paddock, and within that paddock, we have a grain yield map. And then within the paddock further, we have points that have been sampled and tested for things like soil chemical analysis, and we have the results of those analyses for those locations. And all of this is data associated with that paddock. And this data can vary from what I've just described there, from soils and grain yield maps, through to satellite imagery and weather information, as well as paddock management records for those for the paddock. And each farm has many paddocks, and there are many farms within Australia. So there's quite a large volume of data that is being collected across our farming paddocks. There's also data that's been collected now through time across many years, and so we have quite large historical data sets that we can start to look at what trends are occurring within those data sets. And what's important when we look at this data is the quality of that data. So often the data is in formats and rows and columns with numerical values, and we can see that there's the raw data that's generated that might come off of a machine or a piece of equipment or as input from an individual. And sometimes that data is then processed or used to interpolate. So we might have points within a paddock that is then scaled up to a larger data set to cover the whole paddock. And so then we have different versions of that original data set. That's also important to understand which version of the data you're using. And to add to the quality of the data is whether or not there's the metadata that's associated with that data set. Do we know who generated it, what, where, when, and how it was generated? Because that information really lets us understand how useful the data is and how relevant it is for the scenario that we want to apply it to be used for. It's also important to consider if there are missing values or gaps in the data. Sometimes we might only get half a paddock of imagery collected. How do we use the data when we've got those missing values? And for things like machine learning, it can be quite tricky if we don't have consistent channels. It's also important to look at the data standards and whether they've been used. And you might be wondering what data standards are. So I'm going to give a very general and quite easy example of a simple thing like rainfall. Each farm and grower might record that in a different way. They might call it rain, they might call it rainfall, some people call it precipitation. And the data set itself will have that tag associated with that column of data. But when we're wanting to then compare that data set with another farm, we really need to be able to understand what it is that data is. Is it the annual rainfall or is it growing season rainfall? To be able to then compare and link data sets across different farms. And on that note, it's really important to understand whether the data is fair. So is it findable? Is it accessible for someone to use? Is it interpretable? Can you have that metadata associated with the raw data to be able to use that in the correct way? And then is it reusable? Can we reuse that data for something other than the purpose that it might have been originally collected for? So what I wanted to try and do is give an example of how we can use data sets, and the challenge that we've been focusing on in a GRDC focused project is to really understand what's driving the variable crop growth and yield across our farming paddocks. So often there's been a focus on improving our grain yields of our varieties, but when we drive around and have a look at the paddocks, and when we look at a paddock like the one shown here today, we can see that we're not always achieving uniform crop growth and yield across our paddocks. And what we were wanting to do is to use some of those historical mapping layers, so the soil, the climate, the topography, that remote sensing information that's been collected now through time, to see if we can shift away from just zoning paddocks to sort of low and high yielding zones, to really try and understand what was causing that variability in yield, what was causing the plants to not grow well in certain areas of the paddock. Because if we can understand what's causing that variability in yield, we can then inform different management decisions that can help to achieve more uniform yields across those paddocks. So what we did as part of this project was collate a lot of historical mapping layers that have been collected across lots of farms within Australia. We looked at the soil traits and climate and topography and remote sensing information. And we worked with a team of machine learning experts at the Australian Institute for Machine Learning to combine these mapping layers into a machine learning model, which was a causality-based machine learning model. And I'm certainly no expert in machine learning, but I have been involved in this process to really try and extract what we can from those mapping layers to predict yield, but then to take a step back and look at what was actually important for that yield prediction. Because if we can work out what mapping layers were important, we can start to look at what was causing a yield response in a certain area of the paddock. So what we did was we applied the machine learning model to many paddocks, and this is an example of a paddock where we had 3 years of information collected across that paddock. And then we can look within that 1 year of the paddock that was tested to look at all of those soil traits that were put into that model. So if we've got 150 soil traits, we can look at the ones that were really important for the yield, causing a yield response, and the ones that were not so important. We can then pick out one of those traits, and I've got an example here of the EM38, but this is not a map of the EM38. This is the EM38 value across that paddock and how important that was to driving yield. And that's an important difference here. Take one step further, what we can do with this information now is to start to look through time how important, say, those 150 soil traits were across different growing seasons. How do they vary? Which ones are always important and which ones vary between seasons? And then we can spatially map that. So as an example here, how important was the EM38 trait to driving grain yield, and how did that vary through time across those multiple years? And we've now used those outputs from the machine learning model to develop a demo app where we can now showcase what we have been able to observe visually as an output from that machine learning model. And so I'm just going to quickly describe a bit about that demo app so you can see an output from the machine learning process. So what we've got here is a demonstration of the app. This is just showing the yield of the paddock, and this is the raw data. So this is the yield that was collected in 2007. And we can then flick across and have a look at the yield in 2005, just to see that change in yield. Now we can then go down and have a look at a trait of the soil on the side here, such as the sodium in the soil solution in a year. And again, this is the raw data. This is the value that was collected at the start of the soil profile, so at 5 centimetres. We can then work down the soil profile to 80 centimetres and have a look at how that sodium in the soil solution is changing. What we can then do is have a look at how important that trait, so how important is the sodium in the soil solution to causing a yield response. And so in the topsoil layer, in this example at 5 centimetres, it wasn't very important. We went down that profile down to that 80 centimetres. That's when we can see from the output from that machine learning model that this area was really important for driving that variability in grain yield. We can then look at this in a little bit more detail and click on a specific area within this location within the paddock to even have a closer look to look at the actual values of the sodium in the soil solution at the different soil depths, and to check which traits were really driving the cause of that yield difference within that location and the priority order of those traits for that location. So what we were able to do as part of that project was really bring together our growers and agronomists and researchers to share data at that paddock scale, to be able to use that to develop a relevant machine learning model that has useful outputs in terms of being able to actually identify the cause of variability in yield in our paddocks, and to have this now available as a demonstration to show what we can do with the machine learning model and how it could be used by our growers, agronomists and researchers going forward. I'd really like to thank all of the people who are involved in the project and the work that I've just described today, and certainly I'd like to thank the GRDC and the Australian grain growers for supporting this research. Thank you.
Thank you, Emily. Rhiannon. I want to now move into a period of questions. So we're going to sort of tackle it in two parts. So we'll do the questions around Emily's talk to start with. So that's the ABARES productivity numbers and the industry crop and export forecasts, and then we'll dip into the discussion around the technologies after that. So are there any questions there at the moment for Emily? None that I can see, and I'm going to kick off with a question of my own. So Emily, in the current crop forecast, you have sorghum being third highest on record. With these current wet weather, how do you think that's going to affect the sorghum forecast?
Hi there, Terence, and thank you for the question. Well, what we know is that flooding in Queensland and New South Wales has caused significant damage, and our thoughts are with the communities affected. At this point in time, it is too soon to tell what the full extent of the damage is and how it may affect sorghum production. So of course, we'll be closely monitoring the situation. Thank
you. And also, last year you had canola being at record 6.2 or 3 million tonnes. Do you know what crops canola ended up displacing last year? So as in canola production for the 21-22 forecast year? Yes, that's correct, yep.
Sorry, would you mind repeating the question for me, please?
Yes, so canola was at record levels.
Yes.
What other crops were wound back for that canola hectares to increase?
Well, for canola hectares to increase, really what we found was that there was a slight fall in area planted to barley. And this does relate to our exporters, our barley exporters being locked out of the higher value Chinese market. And so that's essentially it. However, moving into the next cropping season, we would expect that if canola areas remaining high, that barley area will again be below our 5-year average.
Great, thank you. We've got a question here for Tim, so we might jump into a few of the technology type questions. So Tim, one challenge for satellite imagery is differentiating between closely related crops, so barley and wheat, probably triticale, those similar cereals, if you like. How is it that how are the evolving technologies likely to increase that level of differentiation between those crops?
That's an excellent question. Thank you. There's a couple of, we're doing a project with UQ and GRDC at the moment, and getting discrimination differences between wheat and barley accuracies well over 80%, and that's due to just better machine learning, but also I think as time goes on, we'll get better, more wavelengths of light to discriminate. We've also found good correlations with other satellites like radar, for example, providing very good discrimination between wheat and barley. So I think as we see the availability of sensors improving, we will see that discrimination accuracy increasing, and we're very confident that we can get that up to over 90%.
Can you add a little piece onto that about when the accuracy really comes into play? Like, are you up, up around flowering, or can you detect those differences in crop at an earlier stage than flowering?
Yeah, we are working on the earlier stuff, obviously, but yes, as the crop progresses towards that flowering point, that is where accuracies are highest. So yeah, the earlier you go, the less accurate you become. But we're certainly working very hard to get those sort of crop forecasts as early as possible, because people want to know as early as possible. So yeah, I think there's still work to be done there, but there's promising signs. I mean, a lot of the work that's been done in the past is almost post crop. So I think the regularity of satellite data will increase that capability and relevance, and as we see more sensors coming, that discrimination will be able to be done earlier and earlier.
Thank you. So the 80% differentiation was for crop the 80% was for crop differentiation. But how about the accuracy in forecasting yield? What level are we at with that at the moment?
There's still a lot more work to do there, and once again, researchers are looking into this, and they've developed some really quite simple models to deliver yield quite accurately. But yeah, there's still a lot more work to do, and really we've only done work on wheat at the moment, so I think there's a long way to go in that space. But we're trying to find models that have very small number of inputs, because the more inputs that we have, the more data we need to build those models. So working with the UQ researchers have shown that with some simple crop stress indicators and some satellite imagery indicators, we can get accuracy of yield quite high. So, but again, there's a lot more testing, and it's early days in that work.
Okay, we've got a question from the floor. So, what are currently the greatest challenges in utilising satellite imagery to obtain agricultural data?
The biggest problem is cloud.
So what do you see as the major constraints?
Yeah, cloud. We can't control the weather, unfortunately. Can't get rid of those pesky clouds. But that's where radar is coming into its own. Radar is not a direct replication for spectral imagery like we normally use, but radar penetrates. It's an active sensor, so it's actually pushing out radar signals. So it's actively pushing those out, so it penetrates through the cloud, and we can detect what's happening underneath. And you've probably seen the not so nice use of this the other day in the Ukraine crisis at the moment, where they're detecting rocket launches at night time using radar remote sensing, very high resolution radar remote sensing. So those technologies can work through the night, through the day. They've been used in the past for things like cyclones, where you just got continuous cloud cover, but you can penetrate through and see the damage that's caused by the cyclone. So, those technologies are increasing, and there's more and more supplies coming online every day. What we've got to do is the R&D to actually understand what it's telling us. And that's the big missing piece. It's quite easy to launch satellites, but to make sense of the data is still a lot of work to be done.
Thank you. That's great. Thanks, Tim. So next question is for Craig. So Craig, you talked about the difference between potential and actual yields in your work. So plant available water or water in the profiles are a big thing for yield. So what have you found? How do you go dealing with water in some of those models that you're looking at, and what other factors are in there that are really driving those yield changes?
Yeah, I guess, well, some of the work that we've sort of done in the irrigation type industries is where we've used sensors to sort of interpret the crop's response to water, and to sort of pick up a little bit on the discussion so far is that using multiple data sets, so not just using a satellite image, but using machine vision data, soil moisture data, and other things that allow you to qualify how the crop is responding relative to those various things that you see in the field. So using, again, through AI, artificial intelligence and machine learning type models, basically simulating the crop relative to, to the environmental factors, but then using sensors which then qualify those models to then fine tune what is actually happening. So we've had technologies deployed on commercial centre pivots where we might be using machine vision to look at the crop. We're modelling the crop in terms of what its resources and requirements are. And then by looking at the field and actually being able to extract parameters out of machine vision technology, we can then fine tune the farming inputs to maximise yield. So, in those cases, what we've done is increased our water use efficiency by 10% and improved our yield by 10% over a standard practice. So that's kind of how we've approached those sort of things.
So a bigger question again for you, Craig, is when it comes down to data privacy and ownership and utilising data from different areas, what do you think are the major constraints in that area, and how does data privacy work in that scope, if you like?
Yeah, well, I think probably the main thing there is access to data and having the confidence to provide that data to others that can then use that to develop the analytics. And that, for me, is where there's a challenge. The quality of the data is also an issue at times. So it's not just providing access to that information, but what's the quality of that information, and sort of talked about that as well. So for me, I guess, it is about providing confidence that if that data is handed over, how is that data going to be utilised in a way where users can extract value out of it without being exploited. And I think, just looking across into the US scene a little bit, one of the things that the US agricultural sector has done is spent a lot of time trying to interpret data agreements so that when you enter into a data agreement, it's already interpreted as farmer friendly, so it gives you some confidence to exchange that information so that it can be used. So for me, that's one of the impediments at the moment, is handing over information and not knowing how it will be used. But if you're signing off on agreements that are already being endorsed as being farmer friendly, then hopefully that gives you some confidence that that information will be used for good.
That's great, thank you. Rhiannon, the next question is for you. So you talked a lot about some of the technologies and the different data that were looking at yield and looking at yield prediction. So out of all of those technologies, what are you finding that are the things that describe most of the yield variance from those data sets you're looking at?
Yeah, so we can see that it varies for each paddock, but I guess what we were trying to get to is a point of a lot of the time at the moment, growers are collecting a lot of data, and we've got to start to realise if there's certain types of data that they could be collecting as a minimum, and because it's taking up a lot of their time and resources to do that. So the example I gave of 150 soil traits that have been used in the model, and we can identify now the ones that are recurring as being important. So we could start to actually focus on them going forward, and maybe with the others, not monitor them every year, but just monitor them every now and then going forward. And that will help to reduce the time and investment that we have, and also that curation and storage of that data going forward too. So I think it will come down to individual paddocks. Once you understand what is driving that yield in those paddocks, then you could start to tailor which mapping layers to be collecting more frequently than others.
Are you seeing variation in different soil types or regions? So let's say your EM38 numbers, is it working in some regions better than others?
Yeah, we are, and that's right. It is often being driven by that soil type within those regions, and I think we're still at an early stage with that project. But I think we could start to certainly tailor, and I guess where we're going with that work is to start to tailor the management decisions that we can alter in those certain soil types and textures.
Great. Okay, I'm going to open it up to a much bigger question, and just ask each of the presenters, and we'll start with Tim. So Tim, in your mind, what do you think the government can do to facilitate more of these data platforms and frameworks, data frameworks coming together to be able to integrate data and analysis better?
I think what the NFF's doing with the data privacy, sort of ag data standards and privacy, is really important first starting point. That way everyone's got a little bit more confidence. I think, one thing that really bugs me is governments and universities in particular getting in the way of commercial providers and creating market failures. We can't afford market failures in this country. It's just not big enough. So I think everyone's got to learn to swim in their lane a bit, and that will encourage collaboration a lot more than what's happening now, because everyone's trying to trip into other spectrums, if you know what I mean. So, you know, we're seeing, you know, a lot of commercialisation spin-offs out of universities, SRO. I mean, I'm doing my own R&D, crying out loud. You know, it's crazy. We need to, if we actually swam in our own lanes, we would get much better outcomes. And I think GRDC, in my opinion, has taken a real lead role in this, in changing the way we think about this, and AgriFutures is absolutely following up. And CRDC has actually probably been doing it maybe the longest. So I think the RDCs are really leading this forward, and that will help much quicker, much better commercialisation and research, in my opinion.
Okay, thank you, Tim. Craig, do you have an opinion there?
Yeah, I guess Tim sort of touched on the main issues, which was, you know, standards and providing that access to that information, I guess. And I do agree that also addressing where that market failure is really important. So that's where governments can have the most input, is to look at the landscape and understand where there's a particular opportunity that's just a market failure, and how it can sort of remove that barrier, if you like. Just sort of reflecting on the commentary around, you know, the university sector and commercialisation. I mean, I think that what we should all be very much driven towards is technology transfer and getting commercialising our research. And, you know, I've got 11 years working on a corporate farm, and one of the reasons I got involved in the university sector was to rip the research out and get it commercialised. So, you know, it's something that we push really, really hard. I know it's not done well across the sector by everyone, but certainly if we had that approach to get the technology out and get it adopted, then we would go a lot further than we are at the moment. But I think, yeah, I guess probably the main thing around the government input is really about creating that sort of the landscape in which people feel a little bit more comfortable operating. The other thing I'll just mention too is that there's also the other issues that not just directly related to data, but more how can government assist in mobilising an ecosystem of technology developers and providers. So it might not be just about the data per se, but it's about maybe there is the resources there to do something with it, but we need to mobilise the entrepreneurs in the ecosystem to actually do something with that and start to connect, you know, technology developers with what the problems are that industry is trying to solve as well. So that's a slightly
Thank you, Craig.
different edge to what you've asked, Terence, but an important one, I think.
Thank you. Sorry I cut you off there. Rhiannon, further question for you on data standards. You mentioned that a bit in your talk as well. Is there anything the government can do there to tidy up those standards for measurement and reporting?
So I really won't comment on the government. I'm in the SA government in caretaker mode at the moment, but I think it's actually up to everyone with the data to help make it more findable, accessible, interpretable, and reusable. So I think that's something that everyone has a role in. And I think, yeah, if we all work towards that, then we know what data sets are out there, we know who can use them, and we know how we can keep reusing them to make even more value from them. So I think there's certainly an opportunity there, and I'd echo Craig's comments before about we really want to see our research make an impact and to get used, and if commercialisation is a way to make that happen, then yeah, we want to see that happen.
Brilliant. Right, that's a great answer. Thank you. So we'll wrap up the tech session there. I've got another question for Emily on the front. So after a record 2 years of big crops, what's our forecast for the forward year, given what we've done already?
Yeah, well, following 2 consecutive high production years, we do expect winter crop production to decrease, yet remain above average. And some of the factors influencing planting intentions will be around strong prices, subsoil moisture and rainfall at the time of planting. Some other factors at play, of course, will be input costs and availability, as well as crop rotation considerations. As for climate, well, La Nina conditions are expected to persist through to mid-autumn, and according to the latest 3-month outlook, there is roughly a 50% chance of recording average rainfall across most cropping regions. So these sorts of factors do point towards production being above average for the upcoming winter cropping season.
Great, thank you. That's good to hear for the forecast at least. So looking forward to that. So we're going to wrap up there. I would like to thank all the speakers. So thank you, Emily, Tim, Neale from, Emily Dahl from ABARES, Tim Neale from Data Farming, Craig Baillie from University of Southern Queensland, and Rhiannon Schilling from SARDI in South Australia. And I'll just go back through some housekeeping notes here. So the short survey will pop up. So we'd welcome your feedback on the session. Don't forget to chat in the spot with the spotlight exhibitors. And they'll be online for the next half an hour, and keep the conversation going in the virtual networking room after this session. So go ahead and give us your feedback. Tell us what you like, didn't like, and that'll be useful for us for our next session next year. Thank you very much for joining us. Cheers. Bye.